Good morning, everyone. I'm truly excited to be here, and we are very happy that now Ray is part of PyTorch and Linux Foundations, and very much looking forward to accelerate the growth of the community. Now, let me start this talk with a trip in the history lane. We started the Ray journey nearly a decade ago. Here is me with Robert and Philip back in 2016 doing what any typical advisor does best. Hands in the pockets, interrupting students from doing work with annoying questions. Since then, we came a long way. After a slow start, Ray adoption has exploded. The last year alone, we have seen a 7x growth in downloads. And why is that? Well, because unknowingly at that time, we built Ray for today's challenges. Ray is more relevant now than when we first created it. Today, thousands of companies are using Ray, from AI natives, digital natives, and to enterprises. So everything started in the fall of 2015 when two machine learning students, Philip and Robert, decided to take my class, graduate class. And the reason they decided to do so is because they wanted to learn how to build tools for their own research, because the existing tools at that time were difficult to use and did not scale. Also, at that time, if you remember, there was lots of excitement around reinforcement learning. OpenAI demonstrated that reinforcement learning can learn to play computer games at the expert levels and beyond. Google shows that you can use RL to reduce the energy for cooling in data centers by 48%. And of course, in 2017, AlphaGo shocked the world by beating the Go world champion. And we are doing RL research ourselves. Philip, co-author with John Schulman, co-founder of OpenAI, a highly influential paper on trusted regions policy optimizations, or TRPO for short. TRPO is the ancestors of some of the most popular RL algorithms, including PPO and GRPO. And we are using RL to teach for many applications, teaching humanoid robots how to walk, control traffic congestions, optimize database queries, and much more. So naturally, we build Ray for RL to support our own research. Here is the original paper we published in 2018, which emphasizes RL as a main workload. And here is RLlib, the library we built for scaling RL on top of Ray. And as you probably know, RLlib went to become the most popular RL libraries at that time. However, we were ahead of our time. RL didn't catch up as expected, as at least we expected. It was hard for enterprises to deploy in production, in part because sampling efficiency, the lack of accurate simulators for most domains, and difficulties in integrating RL in their existing workflows. Fortunately, RL is such a general workload that building Ray for RL meant that we could support virtually any AI workloads. So for many years, we ended up focusing on workloads like data parallel training, high-parameter tuning, and model serving. And while distributed, these workloads are quite simple. So they did not use the entire power of Ray. However, everything changed with the emergence of generative AI, which led to an explosion in complexity. Training evolved from simple data parallelisms to adding more and more parallel strategies to increase the hardware utilization and accommodate larger and larger models with more and more complex architectures. Actually, last time when I checked, there are no less than 7 parallel strategies. Inference similarly grew in complexity, from simply scaling model replicas to supporting things like disaggregate prefill, prefix avoid routing, and obviously all the above parallel strategies. Finally, the infrastructure went from mostly homogeneous clusters to widely heterogeneous clusters. Today, we have hundreds of types of GPUs and various networking technologies like InfiniBand, Ultra Ethernet, RDMA, and much more. And this is what we built Ray for. The more complex the workload and the infrastructures are, the more Ray shines. So not surprisingly, today Ray dominates some of the most demanding workloads. One example is multimodal data processing, which typically combines pre-processing and post-processing with inference. And each of these stages has different demands in terms of the compute, I/O, memory, and so forth. With pre-processing and post-processing running best typically on CPUs, while inference running best on GPUs. So fundamentally, to support these workloads, you need to run it on a heterogeneous cluster. Well, Ray can take care of that for you. And with the rise of multimodal data, like images, videos, audios, and things are even more complex, with pre-processing and post-processing stages themselves requiring a mix on CPU and GPUs. Again, Ray can take care of that for you. Finally, we are coming full circle. As you all know, one of the largest workloads and important workloads today is post-training, which aims to provide reasoning capabilities, break post-training scaling barriers, and address the data scarcity problems, all some of the biggest challenges in AI today. Now, a key component of post-training is reinforcement learning. And since we built Ray for reinforcement learning workloads from the beginning, it should come as no surprise that today nearly every open source RL framework is built on top of Ray. So Ray's time has finally arrived. It is now. Next, Robert will provide a short overview into why Ray is so general and how Ray fits into modern AI stack. Please welcome Robert, co-creator of Ray and co-founder of Anyscale.
Thank you, Jan. So I want to share two different things. The first is a little bit about Ray's API and where this generality to support so many different use cases comes from. And the second is how Ray fits into the overall AI ecosystem. So on the first point, Jan mentioned that Ray can be used for reinforcement learning, multimodal data, LLM inference, and beyond. And this generality really comes from Ray's core primitives. And there are only two core primitives. The first is the ability to take a Python function and execute it as a task in the cluster. So here I have a couple Python functions. I can add this ray.remote decorator on top. And what that does is now when I call one of these functions with embed.remote, instead of executing the function locally, it submits a task that gets scheduled and executed somewhere in my cluster with the appropriate compute resources, right? Maybe it needs a GPU. And so it submits the task and then immediately returns a reference to the eventual output. And because it returns immediately, I can submit another one in parallel, and they'll execute in parallel, right? And when those finish, their outputs will be shipped under the hood to wherever the downstream task is being executed. Could be on the same machine, could be on a different machine, or could have different compute requirements. Right, so this is the ability to take a Python function and execute it in a cluster. The second primitive is the same thing, but for classes. The ability to take a Python class and instantiate it as an actor process somewhere in my cluster. So here's a Python class that creates a model and does inference. And I can add the ray.remote decorator like before. Now when I instantiate this class, instead of creating a local copy of the object, it creates a new actor process somewhere in my cluster. And then I can invoke methods on it. And I could create thousands of these. I could create hundreds of thousands of them. They can invoke methods on each other. They can talk to each other. And now you have the building blocks to build quite complex distributed applications. And so why can Ray support so many different use cases all in a common framework? Well, the reason is that Ray is not really introducing new concepts. Ray is taking existing programming concepts, functions and classes, and just translating them into the distributed setting. And you can build anything with functions and classes. So that's where the generality comes from. And these core primitives are really the basis for the rest of the Ray ecosystem for RL and multimodal data and so on. So the next thing I want to talk about is how Ray fits into the broader AI ecosystem and the PyTorch ecosystem. So Jan talked about, So Jan talked about the growing complexity of different AI use cases, right? Post-training, multimodal data. There's a lot of complexity here. And we are also seeing a lot of growing complexity on the hardware side, right? There's more scale, more failures, more heterogeneity. And because you have growing complexity both in the applications and in the hardware, there's a growing need for a software stack that connects the applications to the hardware. And that software stack has to solve challenges like scaling, reliability, heterogeneous resources, and so on. And so I want to share our view on some of the different layers of this stack. So the first is the training and inference framework. Everyone knows PyTorch. PyTorch is the dominant deep learning framework. And this layer is responsible for running the model efficiently on the GPUs. But it's not just PyTorch. You've got a rich ecosystem around PyTorch for parallelism strategies, model sharding, for optimizing for transformers, right? But fundamentally, this layer is responsible for squeezing the most performance out of the GPUs by running the models. So the next layer is the distributed compute engine. This is where Ray sits. This is about solving the distributed systems challenges of scaling. Think about process management, process orchestration, and coordination, data ingest and data movement, failure handling, auto-scaling, resource management. Often this runs on top of a container orchestrator like Kubernetes. And this layer is responsible for provisioning compute, for handling coarse-grained multi-tenancy. Think user multi-tenancy, job multi-tenancy. Now, one of the most exciting things for me as we've seen this stack emerge over the last year is not just these layers forming independently, but actually these layers co-evolving with each other to better support complex AI use cases. And I'll give a couple examples of that. We all know how complex LLM inference has become. Now, doing a great job with LLM inference requires doing a good job not just at the inference engine layer, but also at the process orchestration layer. Think about very large models. And so by marrying or deeply integrating Ray and VLLM, we've been able to provide, the open source communities have been able to provide very fine-grained control over the placement of VLLM workers. This enables better support for cross-node parallelism. Think pipeline parallelism and cross-node tensor parallelism, or prefill decode disaggregation, or prefix-aware routing. Right? There's a lot of complexity here, and you can do a much better job by thinking about multiple layers of the stack. The same is true with Kubernetes. So Kubernetes provides very coarse-grained support at the job level, at the container level. Ray is more fine-grained at the process and task and actor level. And of course, and I'll illustrate this with auto-scaling. So both Ray and Kubernetes have this concept of auto-scaling at the node level, right? Adding more nodes or more containers to scale a workload. But by marrying Ray's awareness of the workload and what's going on inside the workload with Kubernetes' ability to manage containers, you can actually provide better vertical auto-scaling where you resize containers dynamically to better support the workload. And this is something that is difficult to do at just one layer of the stack. And this is something the Ray and Kubernetes communities, open source communities, have been collaborating on. And so what I'm excited about here, of course, we've seen so much growing complexity around the AI workloads, around the hardware, and we're very excited for Ray to be part of the PyTorch ecosystem to really build out this stack and help support all of the AI workloads people are building today. So thank you so much.